In the previous video in the series, we talked about the double slit experiment as an introduction to some phenomenon in quantum physics. You can click the card in the top right to watch that video now, or you could watch it when you're done with this one. In this video, we will look more into specific concepts in quantum physics, as well as what some of its uses are. First off, let's start with the name. Quantum physics originated from the idea that the energy carried by light is quantized, or can only exist in certain allowed amounts. Essentially, imagine breaking apart the energy into smaller and smaller pieces, until the pieces can't get any smaller, like a singular Lego. The size of the structure built will always be determined by the amount of Legos, and you can't have some in between. You can't have half a Lego if you're using them properly. All light in the universe must have energy which is a multiple of the smallest packet of energy. Whether it's made out of 3 of these packets or billions, the amount of energy can't be any smaller. These packets are known as photons, and a single photon is the smallest base unit of light. Since quantum physics deals with things at this tiny scale, the smallest scale possible of which everything else is built up from, it was given this name. In the field of science, quantum physics is notoriously hard to explain, so why do we need to study quantum physics? Since quantum physics defines what happens at the smallest level, at the level of atoms or even smaller particles, it underlies everything in the universe, from why the sun burns to why molecules interact the way that they do, and how electrons move through a computer chip. If we want to understand how the world around us really works, we need to understand what is happening at the very smallest levels. And quantum physics defines the laws of what happens at tiny scales, just like biology defines what happens in our body. Not to mention that quantum physics underlies quantum computing, a new way of computation which will be looked at in the next videos. If you watched the last video on the double slit experiment, you would see that light behaves as both wave and particle depending on various circumstances. It turns out that it's not only photons which exhibit this property of being both wave and particle. Everything does, from an apple tossed into the air to an electron circling an atom. Every single moving thing moves as a wave with a certain wavelength called the Broglie wavelength, which decreases as momentum increases. Momentum is equal to the mass times the velocity of an object, so the faster or heavier an object is, the higher its momentum. This means that as an object's mass increases, its wavelength decreases, which is why this effect isn't very noticeable at the scale which we normally see things at. For instance, a baseball thrown at 100 kilometers an hour has a wavelength on the scale of 0.0000000 and so on 1 meters, with 33 zeros. For reference, this wavelength is much smaller compared to a baseball than a single atom is compared to our entire solar system, so it really doesn't matter much on a human scale. However, once you want to do anything on a smaller scale, such as observing a moving electron around an atom, this wavelength increases to a size which is bigger than the electron itself, which is why it is impossible to get a true picture of what an atom or electron looks like. It would be like trying to determine where to hit a baseball when it is flying up and down and around in random directions as it flies towards you. It simply isn't possible. Finally, in the last video we started talking about how at the small scale of photons, it is impossible to know exactly where they are and how they are moving at the same time. This is known as the Heisenberg uncertainty principle, where there is only a certain level of precision to which you can know information about an object. The higher the object's mass, the lower this boundary of knowledge is, meaning that for more massive objects you can get more precise information. Specifically, there is only a certain precision to which you can know both the position and the momentum of an object. The more you know about the speed of an object, the less certain you can be about its position, and the more you know about its position, the less you can know about its momentum. Again, this doesn't matter much for objects on a human scale as these have lots of mass, but for smaller particles like electrons, this has a big impact and makes finding or looking at them specifically impossible. On a human scale, imagine it like this. Knowing an object's exact position is like taking a picture of it, and if you take a picture of it, then you can't know how the particle is moving as you only have a single image. If you want to know how it is moving, you would need to take a video, but then the object is blurry and you don't know exactly where it is at a given moment. Imagine this effect but magnified millions of times, and you see why the uncertainty principle is such a problem. It makes knowing the position of these tiny particles nearly impossible, And even if you were able to pinpoint the general position, the tools which are necessary to do this are so powerful compared to the small particles that it would knock the particle off of its path, making the data inaccurate. For instance, the photons of light which would be required to see an electron carry so much energy that they would knock the electron off of its path, making the observation useless as we still don't know what was happening before we looked at it. In a nutshell, at the small quantum scale, it is impossible to know precisely how an object is moving and where it is at the same time, and everything acts as a wave as well as a particle, with its observed effect depending on its size. As promised, here are the three main equations for the concepts covered in this video. All of the symbols used in the equations are shown at the bottom. You can pause the video now if you would like to look at them. In the next video, we will begin looking into quantum computing with a specific concept called superposition, which underlies all quantum physics. So stay tuned for that if you would like to see how quantum physics can revolutionize computers for the future.